will be in, because of at point Q, let's focus at point Q, okay? The P will induce a moment coming in this direction. So this is moment at point A, okay? So by applying Newton's third law, action equal to reaction, same in magnitude, different in direction, we know that we need to have a counter moment, and this counter moment is at point Q. And because the fact that it's going in a clockwise direction, this is equal to minus Py, okay? Force multiplied by perpendicular distance, okay? So from here, therefore, okay, from here we can see, therefore, right, moment at Q is equal to minus Py. Okay, the moment at Q is minus Py to counter moment at point A, because it's force times perpendicular distance. Okay, and we know that it's negative because it's going in the clockwise direction. Okay, now from here, okay, from here, before I go from here, what we are trying to determine now, okay, what we are trying to determine now is, what is this y? Okay, we need to know this y because we need to counter. We need to know the moment at point Q. Okay, so just quickly, if there's no buckling, okay, when there's no buckling, we only have what? Py. Okay, when there is buckling, right, we have P also, but we also have a what? A moment. Okay, it is the resistance of the moment to prevent buckling. You realize, no doubt it's under axial loading, but when the structure it starts to buckle already, you have a perpendicular distance now. So now your structure has to counter what? Has to counter the moment. Okay, I repeat again, it has to counter the moment. Okay, so from here, we are going to apply. Okay, we are going to apply the elastic curve equation to relate bending moment to deflection. Okay, so the elastic curve equation, it states that the Young's modulus and the second moment of area multiplied by d squared y over dx squared, and this will be equal to moment as a function of x. So this is where this equation over here is what we call the elastic curve equation. Okay, this is what we call. Now, before we go back into buckling, okay, I want to show you in detail how this elastic curve equation works. Okay, then we're now going to do a sidetrack because you guys have not seen this before. Okay, we're going to sidetrack. Okay, sidetrack means we're going to a side, and we are now going to look at application of the elastic curve theory. Okay. Now, in order to apply the elastic curve theory, okay, it is important to identify boundary conditions. Okay. It's important to identify boundary conditions. So there are 4 boundary conditions that you all need to know, and it always follow in this sequence. Okay, and later on, I will tell you why this sequence. So what we have is V M theta Y. Okay, so V is our shear force. M is the bending moment. Theta is the slope of deflection. And Y is the deflection. Okay, so we have V, M, theta, Y, and always in this sequence. Okay, so we are now going to focus on boundary conditions. Okay, boundary. So we usually handle, I mean, at this stage of your undergrad degree, there's usually 3 configuration or support system that we will always see. Okay, so the first one is what we call simply supported. So in simply supported, so this is our structure. Okay, and over here, this is our point A. There's pin, and this is point B. Okay, so this is a simply supported structure. So on a simply supported structure, for example, we can have different type of loading. So we can have a point load. Okay, so P over here. So this is our point load. We can also loading system that looks like that. This is known as a gradient distributed load. And you can also have loading that looks like this. And it's what we call our evenly distributed load. Okay. So for this case, we usually take the left-hand side to be x is equal to 0. And then we have a certain distance. This distance from here to here is L. And then we have x is equal to L. Then we write down the boundary condition. V, M, theta, Y. V, M, theta, Y. Okay. Now the next thing I'll do is I will sketch the deformation pattern. Okay. So this is just a sketch. So we are going to sketch out the deformation pattern. The deformation pattern, for example, looks wrong color. The deformation pattern looks like this. Again, this is just a sketch. Okay. So a boundary condition has to be situation that you know what is going on at that specific point. Okay. And we know that at point A, okay, so if I'm going to draw the reaction force, we are going to have a AY, and then we are going to have a BY for reaction. Okay. So do we know the shear force at point A and point B? We don't know. Okay, so down here, not a clue. When X is equal to 0, X is equal to L, we don't know the shear force. So when you don't know, it is not a boundary condition. Now at point A, the moment at point A is equal to 0. At the moment at point B is also equal to 0. Now, I don't want any of you to memorize all this is y is equal to 0. I will help you remember y is equal to 0. Okay. The next thing is y x is equal to 0 and x is equal to L, comma, moments are all equal to 0. Okay. So let's focus at point A. Okay, so now we focus at point A. All right. So this is our point A. And then originally at point B, we have a what? We have a roller support. Okay. Now, if we were to immediately remove the support at B, okay, we remove support at B. What will happen to the entire structure? Anyone? Okay, I repeat again. What will happen to the entire structure now if we remove support at point B? Anyone want to make a guess? I hope you are still awake. Yeah, it will rotate. Rachel, well done. Okay, so what is going to happen is the entire structure will swing downwards. Yes, yes or no? When we remove, will swing when support at point B is what? Removed. So when that's the case, moment at point A is equal to what? 0. Okay. Likewise, if now we have support at B and remove the support at A, right? The structure will rotate. That is why moment at B is also equal to what? Equal to 0. Okay. Now, the next thing I want to define is what do we mean by slope? Okay, so we go define what do we mean by what is theta? Okay. So we know that if this is our y, this is our x, right? And then this is a curve. Okay. And then if we were to pick a point down here, okay, the slope is basically a tangent. Okay, so basically it's a tangent to the deflection. Okay. Go on. And then if I were to sketch a